So thank you so much for having me here. It's actually my first time visiting the University of Chicago, and I'm impressed by the whatever Harry Potter architecture. I guess it's the Oxford-looking kind of architecture. Yeah. Today, okay, it wasn't. I had an interesting flight last night, so yeah. And I'm coming from Phoenix, so I believe that's one thing we can brag about is like the Phoenix sun, right? But today I'm going to talk about scaling geospatial maps. Let me give you a little bit of perspective. What we do at the Data Systems Lab, we basically at the Data Systems Lab at ASU, we kind of design and develop experimental software systems, and more specifically, data management systems. And the umbrella they're working on these days is again geospatial data. So how can you build like scalable, efficient data management systems that support geospatial data processing and analysis? Okay, so geospatial maps. So maps, we have been already like using maps for centuries, right? So and it's been these are one of the earlier maps that we had back then. And it doesn't look that different than the maps we have. If you look at just at the image, that much different, especially if you look at the last version of it, or the tabula ruggieriana. So we kind of have, since the Mercator projection, the maps looks the same as it used to be, but it has been guiding us, guiding humanity in general. Fast forward to the year 2000, and I'm not sure if you remember that piece of news. So that was in the year 2000, and President Clinton actually he freeze the GPS signals, and that means that was actually almost the first time that we, as regular people and like commercial institute, can we use the GPS signal the same accuracy as the military. That was kind of not a thing before then. So that was kind of a history made back then, and we all witnessed the huge impact of such decision today. But this is, again, the talk is not about politics. I'm just saying the piece of news because put things in perspective. So maps, that led us to the maps in the internet era. And again, a lot of people utilize the GPS technology to build really very useful applications. And now we have Google Maps, we have Bing Maps, we have Yelp, OpenStreetMaps. These are just a few applications of what we have these days, but they have huge impact of our lives. And actually, some of us cannot, like I believe everybody else use Google Maps or Apple Maps or Bing Maps at some point, and we're still using on a daily basis. So I call this the map of the internet era, but these are not the maps we have today. So today, if we look at our planet, so we have a lot more information that is added to the map. So for instance, like billions of mobile devices, it's becoming mainstream. Everybody has a mobile phone. If you look like 15 years ago, it was not the case, but now it's like everyone. We have wearable devices. We have tons of sensors, and that's actually the initiatives about smart cities, and one of them is in Chicago here. We have traffic intersections. We have a lot of sensors. So we also have like self-driving cars. A lot of initiatives, people are experimenting with them. And not even with self-driving cars, the existing cars have a lot of sensors already. They're collecting a lot of information. Drones as well. We have also like Facebook users or social media users. They're also using, they're like posting information on the map. We have smart home. We have the smart city. So all of these information are added to the map. And you can quote me on the following. So everything we do these days leaves breadcrumbs of geospatial digital traces on the map. Everything we do, okay, with our mobile phone, on the internet, it leaves digital traces on the map. And again, so we have this huge amount of data and the maps, and it makes this like a really big map. So the map looks the same, but the information underneath is huge. So the applications that we can run on this is a lot. So there are already tons of existing applications on the map. So we have the user here at the center, and find a taxi to transport a person between point A and B. And of course, we have Uber and Lyft these days, and this is kind of the main, it's kind of, a lot of people are using these applications these days. We also recommend me a sushi restaurant, right? Or find a bar that my friends or friends of friends checked in or liked before. This is also an application that uses such information. More scientific or like policy applications find the correlation between traffic and air pollution. That's one application also is really important for government and policymakers. Measure the water waste in Arizona. We don't have a lot of water waste in Arizona as it is in California, but that's also one interesting query we can run. And visualize the distribution of electricity consumption in the United States. And these are just examples of the applications on top of this data. There are endless applications. There are so many challenges to support these applications and other future applications. But the main challenge is actually in the data infrastructure. When you talk, like, I was giving a talk at Uber recently, and I was asking them what kind of data infrastructure you're using. And then, I'm not sure if you guys are following, they were using Postgres and then moved to MySQL, and then now they're struggling with MySQL. It's like, it's a mess. The operation is running, but they still need to scale. So they say that the existing or state-of-the-art geospatial infrastructure, it's either not scalable, or if they go to non-geospatial data infrastructure, talking about database systems or data management systems, these kind of software, they do not support geospatial data, or they think geospatial support is kind of an afterthought. It's like everybody go talk to everyone, is saying, oh yeah, I have a database that can support anything, right? So which might be true, but these people, geospatial data is their life, right? And they don't find what they need into these platforms. So the first challenge in data, like building a data infrastructure, is definitely scalability. And we looked at the data that we have on the map these days. So we have the volume of available geospatial data is really large. So we haven't, like back then in the maps that we have back then, I'm talking about like original maps, all the information on the map is really small, right? But these days it's like getting really huge. And not only that, the size itself is a challenge, but it's not the only challenge. This data is actually growing at a staggering rate. So we have a lot of data coming in on a daily basis, on a second basis actually. So how can we build a data infrastructure that can support that or can address that challenge? Another challenge which is also related to scalability is interactivity. So let's assume that I built a data infrastructure that allows me to store and digest this amount of data, okay, geospatial data. How can I support the application that I just talked to you about in an interactive way, like sub-second response time? Again, when the data is super large, it's not easy to do that. So enabling interactive performance is also very important for either end user applications or even analysis applications, because you can reduce the analysis time. All right, so given this outlook, here are like a couple of projects I'm going to be talking about that address some of these challenges. So again, we're going to talk about like one way to scale spatial data indexing, spatial data processing. We're talking about running query processing or data processing operations, and spatial data visualizations. For some of these projects, I'm going to talk about some details. For some of them, I will just scratch the surface a little bit, because I have a lot of slides, so I hope I can accommodate everything, right? So first, I'm going to start from the bottom level here, which is spatial data indexing. So this is a screenshot of a real data set. This is a New York City taxi trip data set. This data set has been popular in the past, I would say like past year or something. So it's a 260 gigabyte of the released New York City taxi data, and between the year 2009 and 2015. We built that heat map on the whole New York City trips data. And the question is, if you have this data and you want to store it in a database, how can you do that? there are definitely existing ways to store data in the database system. But the assumption is that this is just a snapshot of the data. If you have an Uber application, the data, the size of the data is even way larger than just hundreds of gigabytes. It gets to terabytes level, even more. So how can you store such data? Simple way of doing it, you have a database system, like let's say Postgres, if you guys are familiar with it, with any relational database, for instance. That's one way to represent it. So you have a pickup time, pickup location, and all the attributes about the taxi trips, fair amount, for instance. Okay? And database store data in like a heap file like that, for instance. So these are just a simple, very straightforward way of storing data in a database system. Okay? So we have data pages in the heap file, and then the tuple information are added into this heap file. Very simple. So far, this is how existing database systems work. And let's assume you want to insert new data into the database system. So you have a new taxi database record. It's added in this area. You add a tuple, and then you find an empty page, like empty slot in a page, and add it into the heap file. So far, nothing new. But let's assume you want, most of the time if you have spatial data, sometimes you want to pose what we call spatial range query. Okay? So a range query in this case is that you want to find all taxi trips that lie within the LaGuardia airport kind of area. Okay? To do that, you either scan the whole data, which is all database, like all database people know that this is not the best way all the time, especially if you have a very high or like a high selectivity of the query. So you build an index. Okay? So indices, generally speaking, look that way. This is an abstract way of looking at index. You have index entries that helps you search through the values that you want, and you have data entries like that. The data entries are tuples to where the data exists, like the tuple exists in the heap file. Okay? So it's think of it as a pointer to where the data is in the heap file. So as you can see, these indices exist. An example of that is B plus tree in database systems. If you're talking about spatial data, there's an R tree. There are different, like there's a quad tree, KD tree. There are different index structures that we have invented over the course of, like if we're dealing with geospatial data in general. Again, these indices provide a very high, like reduces the latency of the query. So it's very efficient when you run the queries. The queries are very fast, because you can easily navigate through the data and get to the block of data that you have. But what are the problems with this existing data structures that we have? First problem is that the storage footprint of these index structures is huge. So if you talk to, again, somebody who's working on database systems, they will tell you a B plus tree or an index in general exhibit like 10% storage overhead, right? When I did this myself in a database system like Postgres, like building an index, like a B plus tree index takes like 20% of the 20% overhead as compared to the existing original data that you build the index on. If you're building a spatial index, like an R tree, for instance, in Postgres, it's actually, the overhead is even 50%. This is practically speaking based on data that on this data set, for instance, that I worked on. So huge storage overhead. Again, a lot of people will argue storage is cheap, so I don't care about it. But if you are storing the database in like one of the modern storage devices that we have, okay, may not be as cheap as you think it is, right? And if you're storing the data in memory, for instance, the indices in memory, this is not as cheap, okay? So that's one challenge, but it's not the main challenge. A very important challenge is the update or the data ingestion rate. These indices are very slow, practically speaking, and I will show you numbers. Very slow because you have to go and search through all these index entries in order to find where to insert that new taxi trip. And for Uber, for instance, this is not working. So if you're building an index and you want to update it for each inserted index entry, okay, or like use the update strategy in these indices, it never works, right? So it's not going to scale, it's not going to ingest the data, like just the data at that rate. So one simple idea of dealing with that is, first of all, the storage overhead. As you can see, the problem with the storage overhead is that the data entries. So one way is to drop the data entries. So let me talk about the goals first. So the first goal is that we want to build a lightweight index, so small storage footprint and low maintenance overhead. But on the other hand, we don't want to hurt the query execution performance. We want the comparable query execution performance as that to the R tree and the existing, or the V tree, or any of the existing index structures that we have that provide good execution time. So we have, that's one project we've been working on how to do that. There's a paper about it in VLDB, and demonstrated also in ICDE this year. I'm going to tell you the idea. Very simple idea, but very effective. Again, this is the same figure that we had before about the index. One way to reduce the storage overhead is to drop the index entries. This way, because the index entries you have, if you have a billion tuples, you can have like also the same order of pointers to where the data is. So you can drop that, and instead of having a pointer to the tuples, you have pointers to blocks of data instead. However, there's a problem with that, is that you're losing the direct pointer to where the data is, and hence you can lose a little bit on the query execution performance. In that case, what we did is that we introduced a data structure. Again, the data structure is a flat data structure, not a hierarchical data structure, and it has a set of n index entries. Each index entry inside the data structure has two main parameters. Okay, the summarized page range, which is a set of pages on disk that are summarized by this index entry, and then a histogram-based summary. We leverage the histogram that is already maintained by existing database systems for query optimization, so there's no overhead of building that, it's already there. And we cache the data distribution in this case. So the data distribution in spatial data, for instance, is like how data is distributed over space. But this can work also for one-dimensional data, or like traditional data, not necessarily geospatial data. So this is the page range is also dynamic, but it only summarizes contiguous pages on disk, or contiguous like data blocks. The histogram-based summary, again, we get like different histogram buckets, and we store it in a compressed bitmap format, so that we again have actually very compact storage of this index. So again, this is represent the histogram-based summaries in spatial data. As you can see, you can have multiple buckets. This is a very simplified way of explaining it. And then each page range represented by different partial histogram buckets, as you can see. So how can the query processing happen in this case? Let's talk first, like this is how we build an index, but we also, again, to further optimize the storage, we group pages that are similar together, but that are contiguous and similar together into the same page range, so that we can even compact the storage even more. And the query runs like this. So first, you have two steps, very simple steps. Scanning the index entry, you scan the index entries in this Hippo index, and then you filter the false positives. Because again, as you scan the index entries, there might be pages that are false positives. So we filter the false positives, and then we pass the page IDs to, for example, the databases, like let's assume we're implementing this inside Postgres, which we did. We pass these page IDs and then to Postgres, and Postgres return the tuples as the answer, right? So these are the two main, and you keep doing this for each index entry in Hippo. Data insertion. Data insertion is way simpler than it is in existing index structures, like I'm talking about R tree or B tree. So because once you have a new tuple inserted, let's say a new taxi trip that is inserted in the database, in the table, you go ahead and you figure that there is new data inserted. The database system will tell you that. You go and you find the affected index entry, and all what you need to do is that load this index entry, update the summarized histogram-based summary if necessary. Okay, if it's not updated, just move on, right? And that's all about inserting a new data. As you can see, this can actually achieve way high ingestion rate than it is compared to the R tree, for instance, or the B tree. What about deletion? So some applications request deletions. Uber application or like taxi trips, people don't necessarily delete, but some other applications request deletion. So what do we do with deletion? So with deletion, we don't need to actually eagerly update the index with deletion because we have a filter false positive step. So if there is any data deleted from the index, even if we don't update the index entry, we're still going to catch the right data from the disk pages for in the filter false positive. However, if you wait a long time before you delete, the query response time will be affected because the histogram-based summary will not be a real representative of the data that it summarizes. So this is where we have like we do the deletion in batch, but we really summarize only a portion of the index entries that way. So let me show you a little bit of experiments of how this performs as compared to a de facto index structure like the B plus tree. So again, we loaded the data into Postgres. We first implemented this inside Postgres 9.5, and then we loaded the data into Postgres, the New York City taxi trip data set. And let's look at the storage overhead. So Hippo, this is our index that we're proposing, indexing scheme. It's actually 1 gigabyte. That's the storage footprint, while the B plus tree is 40 gigabyte. Okay. Initialization time, as you can see, also is smaller than that of the B plus tree because it's one scan of the data and you build the index. Okay, as compared to the B plus tree. So we achieve way better storage overhead than the B plus tree, and we achieve way better than the R tree. So the R tree is even worse than the B plus tree in doing the index. Query performance. So, okay, we saved a lot of storage overhead. What about the query performance? We measured the query execution performance by changing the selectivity of the query. And again, the selectivity means that how much data is returned as compared by the query as compared to the original size of the data. So if we are returning 1% of the data, so it is a 1%, this is a selective query, but not quite selective. Still selective, not quite selective. As you can see, we can achieve pretty much the same exact similar performance to that of the B plus tree. The same for 0.1%. When we go to 0.01%, we can see here that the B plus tree achieves better query execution performance. And again, for much lower selectivity, the B plus tree is better than Hippo in that case. But we say this is acceptable in some applications, in some applications it's not. And let me put the picture in perspective first using the update or the workload, if you have a hybrid workload. Here we show the performance of the indexing scheme as compared to the B plus tree using a hybrid workload. What I mean by hybrid is that you have a workload of, like you have update transactions and you have queries coming to the system. If we only have 10% queries in the system and then 90% updates. Updates mean new index entries added. This is the throughput of Hippo as compared to B plus tree. Like Hippo achieves way better throughput in that case. And for the 50% queries, 50% updates workload, Hippo still achieves better, even if we have 90%. The reason behind that is that the B plus tree maintenance performance is really bad. Data ingestion rate is really bad as compared to Hippo. The query execution performance in a lot of queries is similar, but in very high selectivity, B plus tree is better. So if you look at the hybrid workload, it is better. So the question is when to use Hippo and when to use a B plus tree on R tree. So we have another paper that it's not published yet that has a complete benchmark of R trees like GIST inside Postgres and another index structure called Brin and our index scheme. And we give recommendation of when to use this, when to use that. So if you have an application, geospatial application like Yelp, you want to select the data like restaurants in like whatever at the University of Chicago area to go to dinner. Do not use Hippo. Okay, use an R tree. It is the best because the selectivity is really high of this query, and there's not much updates. Okay, so in this case, R tree or B plus tree will work better, work the best. If you have an application like you want to visualize the heat map, okay, and you want to select the heat map for example, a small range within New York City or something like for the taxi trips, do not use an R tree, right? to use Hippo in that case. Because again, the query is selective, but not as selective as the query of Yelp, okay? And there is a huge amount of data coming into the system all the time, like Uber application, for instance. So that is our observation from what we implemented here.
Excuse me. So
Please.
So I didn't understand the, how are you laying the data out in the data blocks? Is there any locality there? Because if
no locality whatsoever.
So then you're, in the typical case, you're going to end up scanning all the data, all the ranges anyway.
All the ranges, yes.
Yeah.
This is true.
Okay.
So in very, not in a typical case, no.
Yeah.
I disagree on the word typical,
yeah,
but I
no,
agree with you.
Absolutely typical.
Not
right, because you have no control over where the data is going. So it's going to be randomly spread across the file.
It's not random. This is okay. A good point. Yeah, this is a good point. So you have no control of where the data is inserted in any file, right? Which is true. I agree with you.
But you're not doing that. Okay.
You're not doing that. We're not doing that, of course.
Right.
So why we're not doing that? Because it's a huge overhead on building the index and a huge overhead in updating even, right? So what we are observing from the data sets that we input, we actually did this also benchmark on TPCH, and we did benchmarks on other kind of real data sets as well, is that no, you don't have to scan the whole for all the queries, especially if you have, because what we do is that we kind of use the histogram-based summary to prune some of the data. But if you have very large range query, like what I mean, the range query is not very selective, yes, you will have to scan the whole data, or a big portion of the data. But in this case, actually, we don't recommend using an index at all, right? We recommend that you scan the data anyway, right? Even with an R tree or P tree or anything.
But what's your bitmap based on? So
the bitmap is the bitmap is a histogram-based summary of the data represented by the range of the page range.
So a location. So you've got a table. You've got a bunch of columns.
Yes.
You're picking one of those columns to do the histogram on?
Yes.
Which of the columns are you doing histogram?
The column is the column you're building the index on. So again, this is the same way you create a B tree in Postgres, for instance.
Okay.
You say create Hippo instead of a B tree, and you specify the column that you're building it on. Okay. Yeah.
And then as you're inserting things, they're inserted randomly into the heap file, compared to that.
I'm not comparing. Yes. Yes. So if that column, in other ways, if that column is sorted,
right,
you can achieve better performance even, right?
Right, but then a B tree would work well too. You just bulk load it.
This is true, and especially if the B tree is a primary index,
right?
Yeah? Instead of the secondary index.
So I'm not seeing where you're getting your benefit from.
No, we're getting the benefit because again, the storage overhead, we're getting the benefit. Do you understand that, right?
No, because you could do a sparse B tree and you get rid of that lowest level, and that's where all the costs are.
It is, this idea is actually builds upon the sparse index as well.
Right. And
also small materialized aggregates and column imprints even. Yeah.
Right.
But it's not the same. Yeah, but it builds upon it. Yeah.
Okay. Nobody else is.
No. We'll talk about it. Yeah. It's an interesting discussion. But I can show you the results and the code as well to see how it's how it works. Yeah. That's good. Yeah. All right. Let's move on from that point. Let's talk about spatial data processing, and that's where I'm going to be talking about Geospark. So scaling computation on spatial data. So how can we scale computation on spatial data, or scale computation in general? So what we wanted is that we wanted to share nothing system architecture. We want to support parallel computation in memory data processing. So these are the main things that we want to support in order to scale the computation. When we thought about it, we thought that do we need to implement the system from scratch for geospatial data, or can we leverage existing frameworks in a way that exist out there? So we said we don't want to reinvent the wheel. So we looked at the existing systems. We first started with Hadoop, and then we figured Spark fits the needs more, especially when we're talking about in-memory data processing. Spark achieves better performance than Hadoop when it comes to that, and also a lot of the geospatial application has iterative processing. So Geospark, also Spark is better at that. So what we did is that we took Apache Spark and we extended Apache Spark with geospatial data processing operations. So what we took the code, we looked at it, we tried to implement the operations on top of Apache Spark, and it worked, of course, because of, but it's not as efficient. And as we tweak it, we wanted to tweak it more to achieve better efficiency and better scalability. So here's how it works. So again, this is the same data that you have, for instance, and then you go ahead and you distribute. The data is distributed. So Apache Spark has the RDD kind of concept. So it's a resilient distributed data set. We distribute the data across the cluster. What we did is that we had a spatial RDD layer. So what we did here is that we extended the programming interface of the RDD to support geospatial operations. What do I mean by geospatial operations? Like, for example, we had something called the point RDD. We have the polygon RDD. We have the rectangle RDD, and so many of that. So we have different kind of RDDs to support geospatial operations and geospatial data. And these data are kind of distributed across the cluster. So this is from a programming interface perspective, but there are many challenges to doing that. So like, for example, how can you achieve load balancing in that case and reduce the amount of data shuffle and also optimize the local computation for each local machine. So what we did is that we have this spatial RDD layer. We also implemented spatial partitioning. So instead of just using the existing partitioning strategies in Apache Spark, we kind of extended that to support spatial data partitioning, like the different logical partitioning that we use in spatial data. So, and the idea here is that, again, we do load balancing, minimize the global computation of data shuffle. The partitioning techniques that we implemented with GeoSpark are the uniform grid, which is very simple partitioning, and the R tree. The R tree is basically the level before the weight level of the R tree. We kind of cluster the data that way. Quad tree and Voronoi diagram. So these are existing logical spatial data partitioning that exists there. We implemented this with spatial partitioning. So when you load a spatial RDD, like a point or a polygon RDD, you automatically partition the data and cluster it based on the spatial proximity, as you can see. Not only that, so what we did is that we also, for each local partition, we kind of pushed spatial indices, local indices, in order to boost the spatial processing, or the processing of the spatial data on the local machine. So the indices that we created also quad tree and R tree, local indices. So in each node you can have like a spatial index like that indexes all the data in that node, right? And on top of this, there is the spatial query processing layer. It utilizes the partitioned spatial RDDs as well as the spatial indices, local spatial indices, to do typical spatial query processing operations like range query, and it does this again in a distributed fashion and parallelized way as well on top of these. So, and also KNN query, k-nearest neighbor, and spatial join query. We have like KNN join, distant join, and all these kind of operations. And the spatial query processing layer, it also, the way it distributes, so just to show you the code of how it looks, this is a spatial join. How many of you are familiar with spatial join? Okay. So the spatial join is like you implement, this is the same way you implement things in Spark anyway, except that you implement it using point RDDs and polygon RDDs. You want to find all sets of points that lie within a polygon, right? So when you find all the polygon point pair. So this is simply the code to do it. So as you can see, it's like a few lines of code and you get this done. And once you do that, it automatically, again, it leverages Apache Spark, and it automatically kind of does the computation, parallel computation of this spatial join in the cluster. So again, the query processing layer leverages the spatial locality and recycled index spatial RDDs. So to show you just a quick overview of how the spatial join works, as you can see, you have two main steps. So this is again spatial join over the partitioned spatial RDDs. So the step one is that you group the data, you do the repartitioning, and then you do the local computation to get the final join results for each machine. This is way more efficient than it is the workflow of it not using the partitioning. Also, to give you an idea of how the performance of the system works. So we did experiments on like an 11 nodes cluster, and we did this on OpenStreetMap dataset, a 200 gigabyte OpenStreetMap dataset. So the partitioning performance works as follows. So if there is no partitioning whatsoever, you just leave it to Apache Spark to do the partitioning the way it does. Of course, you don't have a very good performance in general. It still scales, of course, with the cluster, but it's not as good as you do partitioning. If you do uniform grid partitioning or Voronoi and R-tree, R-tree achieves a better performance. R-tree partitioning technique achieves the best performance in our experiments on this data set. Again, let's here also increase the number of cores that we have in the cluster. As you can see, so this is, the gray is Geospark without a local index implemented in each partition, and the red is Geospark with a local index implemented in each partition. So the local index, you can see you can achieve better query execution performance that way if you have a local index. However, just for fair comparison, you might have more memory overhead in the cluster. So as you can see, having more memory overhead because of the computation, because of the existent, like you adding indexing overhead, an extra storage overhead out there. Also, this is really important. If you're running algorithms that require geospatial iterations of a lot of geospatial data. So a lot of geospatial analysis applications like co-location pattern recognition, or if you're doing any kind of geospatial machine learning on geospatial data or something, there's a lot of iterations. So as you can see, if you have more iterations, the performance of the system gets better, but then it stabilizes, as you increase the number of iterations. But that makes sense because after a while, the return on investment of the number of iterations is not as much as it is that you have before. So this is basically the performance of Geospark as it is right now. So we have implemented Geospark again as an extension to Apache Spark, and we have the code open source, so you can play with it. Currently, many people are actually playing with Geospark. So we have people from Uber Maps, from Apple Maps. We have even startups that are playing with that, people from academia that are actually using it for real data. Okay, and I would say the good thing about Geospark again is that it does not reinvent the wheel. So it utilizes Apache Spark, which is a very strong engine, right? But on the other hand, it kind of complements it to do the geospatial operations. And that's the good thing about it. So when we talk to people from Uber Maps or Apple Maps, if you ask them to use Spark right away, it's kind of, it was hard for them. But now this enabled them to easily use Spark. And also, it does all the kind of, I'll say the dirty work of efficiency and scalability for spatial data, specifically geospatial on their behalf. So that is the good thing. So it is, Geospark is listed as the one of the third-party infrastructure projects on the Apache Spark. Some of the Apache Spark developers experimented and said it's a good tool to do geospatial operations on top of Apache Spark. So please.
I had a question about the process. Was it only tested on point to polygon joins, or you did polygon to polygon joins as well?
Polygon to polygon, even specific rectangle to rectangle, rectangle to point, not only, and polygon to polygon, and point to point. So we have join on spatial, distance join, K-man join between points, rectangles, polygon pairs. All of that we tested it on.
Would it do calculations on the fly for proportion then? So if you do polygon to polygon, say you're just doing a simple overlap.
Yes.
And one polygon overlaps the other by 80%.
Yes.
Will it report that back?
No.
Okay.
Currently we just have a Boolean, but
okay.
I don't see this. I just want to be.
Or is it proper for that?
Yeah, I want to be exact to you. I see it. We didn't do that. So what we did is that the question we asked in the join is there an overlap between the polygons or no? Yes or no?
That was just binary. Okay.
It was just binary. It's just a Boolean kind of binary kind of decision. but it's a good idea actually to support that.
Okay.
Yeah, but currently, if you download the software, it doesn't support it.
Okay.
Okay. Any other questions? Awesome. Okay. I'll just move quick because we don't have a lot of time. Yeah. So spatial data visualization. So geospatial visualization is actually very expensive. Why not? This is an example. So this is data from NASA. It's the Earth temperature data from 2009 to 2014, month by month. Okay. So this is the amount of data that you have. You have 72 months, 14 billion points per month, and 1 trillion. That leads to 1 trillion points, and you have to visualize that. This is a super expensive operation. Let me just put things in perspective. So what do we mean by geospatial visualization? First of all, there is static cartography, so which is the map generation. You have map servers, we have all of these kind of existing techniques that does generate the cartography, generate the map, how it looks like. And again, this is kind of a static operation. You have static data and you want to generate a static map. There are existing techniques, but I'm going to show you that we also extended Geospark to scale the generation of this static map. Another kind of visualization, interactive visualization is a little different. Interactive visualization means that you have the user is logging into the map and then doing zoom in, zoom out, and kind of panning across the map, doing all these kind of operations interactively with the map. And perhaps the data is also changing, okay, while the user is doing that. So this is a different story, okay? So there is an overlap between static cartography or the map generation and interactive visualization, but again, different techniques are used for each of these. To scale the static visualization, so what we did basically is that we extended Geospark again to do a spatial data visualization. So we have a spatial data visualization layer on top of it. Not necessarily on top, because sometimes you have to do the query processing and the map tile generation at the same time to save the computation, right, and do it faster. So, but from a programming perspective, it is actually on top. So we have scatterplot, heat map, and choropleth map implementation actually on top of Geospark, and it's a package that extends Geospark. It's called Babylon. So just to summarize, what we did is that we have laid down the several operations that are required to build a geospatial map. And these are the main operations, from rasterization to colorization to rendering. And each of these single operations we have implemented in a way that leverage the parallel computation infrastructure in Apache Spark, so that we massively parallelize each of these operations if possible. And not only that, if the data that needs to be visualized as a result of a spatial query, we kind of merged these operations with the spatial query processing as well, so that we can do it in a more efficient way. So again, we have a visualization operator, and you can extend it even to modify your result. Like if you have changed the color of the map, the heat map is different, the scatter plot, or like the dot map, which you want it to look differently. We allow you to do that also inside. I'm going to talk about interactive geospatial visualization. Scratch the surface of what we are doing. We still don't have published work on that, but scratch the surface a little bit of what our idea is how to do it. Again, a Spark or Hadoop solution may not be easily applicable in this case. You need actually a database, especially if you need interaction, right? However, I have to say that some people are working on efforts of how to make Spark or Hadoop as a database, right? There are some efforts on this already that you can also utilize these as a database and do interactive visualization on top. So let's look from an abstract perspective how visualization happens, geospatial visualization. So when I did geospatial visualizations, I have Mapbox, I have Google Maps, for instance, and I want to build a heat map. So what I do is that I have a spatial database, or a database in general. The data is coming to database, and then I go to geospatial Google Maps, write the API to run the geospatial operations, okay? And then I do interaction, zoom in, zoom out, everything. What is the problem with that? Or what are the good things? So the problems, it's not scalable. So if I go to Google Maps and load the data, I want to load the data from spatial database, if I have even 10 gigabytes or 20 gigabytes, I'm assuring you, it's going to crash. Okay, it's not going to work. Okay. So that is the first problem. The second problem, it's when it's super large, even if it's loaded into the Google Maps, it's not going to be as interactive as it is for small data. But the good thing about it is like it's very accurate, also very nice, like very nice visualization, right? Sorry. So our idea is actually to come in the middle between the server, the database system, and the visualization client. So what we have is like, we have a map interactions recorder. So we leverage two main ideas. First idea is, again, sampling, geospatial data sampling. The second idea is actually predicting and prefetching the data for the user, the spatial data for the user based on their interaction history. So we have the map interactions recorder, and then it sends the data occasionally, like in batches to the interaction log, and this is the map interaction analyzer, and it's on the server side. And then you have spatial data. What you do is that you build a tile index, where the tile index is of sample geospatial data. So if you have hundreds of terabytes, of course we're not going to visualize all of this, but we sample it to make sure that we still have accurate visualization and have interactive performance, because we want to send small set of data, size data to the client eventually. Sorry. And then you have the server tile cache. So we have a cache that prefetch the data, the tiles from the tile index, okay? And then this tile prefetcher eventually sent the data to the client, and you have also a cache on the client side, okay? So this middleware is part of it is on the client, part of it on the server. We don't have published results yet, but I'm telling you that if you're doing this with Google Maps, it can scale Google Maps to hundreds of gigabytes based on our experiments on the data. You can do visualization like heat maps, scatter plots, or anything, 200 gigabytes without modifying the JavaScript of Google Maps or anything. Okay. So opportunities, things that we didn't do, but we think it's an opportunity, like leverage GPU accelerated databases. If you're familiar with MapD, it's a startup, and they're doing GPU accelerated database, and they visualize geospatial data as well. So this is the thing that can be leveraged, and also leveraging existing database ideas like materialized view maintenance to support dynamic GeoDa. So materialized view maintenance, if you have dynamic data and you want to maintain the view, maintain the visualization, so you can use kind of leverage the materialized view maintenance. So far I discussed two main challenges: interactivity, scalability, and interactivity. Are these the only challenges with geospatial data in general? Actually, it's not. There is another challenge, which is like heterogeneity. Heterogeneity means the following. So spatial data comes from a variety of sources. So you have weather, traffic, user reviews, social media, and that means that you have geospatial data. So it's our geospatial world, but it does not come alone. There's also other kinds of data, okay? And other kinds of data are as important as the geospatial aspect of the data, like text, graph, relational data, right? So one of the projects that we worked on is how can we support, like integrate geospatial data with user reviews and ratings. So this is location aware. We build a location aware recommender system. So the idea here is that the problem with it is that you have a lot of users, you have a lot of items, and a lot of user item ratings out there. And our original paper on this was, again, like discussing the concept of how to model location with the user reviews and user ratings. Okay, but we faced a lot of, again, scalability and efficiency challenges. And this is why we looked at the database system, how to store the database data in the database system. So as you can see, here's the database system. The way to do recommendation on database system is that people used to do that. So you have the database data stored here, and then at the application layer, you build recommendation, and then you retrieve the data using SQL. Okay. So the recommendation means recommendation model building. This could be machine learning, like singular value composition or collaborative filtering, and then recommendation generation. And this is the query when you do the recommendation. So what we did is that the problem with this is actually every time you need to load the data off the database system to do the computation outside, okay, the recommendation computation. And this is a huge overhead, especially for large-scale databases. So what we did is that this is the on-top-DB approach. We implemented our approach called RedDB, and basically it pushed the recommendation functionality inside the database system. the same way you do SQL, like select, project, join, you do recommendation also on the data if needed. So this is the architecture. Don't bother with the details. I'm just going to give you a quick overview of how it works. The idea is that you have data like this. You have SQL extended. We have like new SQL clause like this that says recommend. Select from the ratings, and instead of selecting the whole data, you recommend a few set of the data from the database. Okay? And you implement the recommend clause. It leads to a recommend operator that is implemented inside the database engine. Recommend operator implements algorithms like one of the algorithms we implemented is singular value decomposition. Okay, so singular value decomposition is a matrix factorization technique. So you have items factors table and user factors table, and you do kind of a dot product on top of these. Okay, so this is again implemented as an operator. So you can, the good thing about it is that you can run it side by side with other database operations like selection, project, join. You want to filter the data based on the location, for instance, using a selection and then do the recommendation on it, on the filtered data. So back to the application we wanted to do is like a Yelp recommendation, for instance, or Google Maps. This is a simple SQL, few lines of SQL code can implement this application. We actually show that you can implement this with few lines of SQL code. And not only that, it's with an order of magnitude faster query, recommendation query performance as compared to the on-top DB approach. So some of the, this is basically what we did. And the system, we have a prototype of the system called RegDB. Again, what we did is that, again, this is a database, but we wanted to reach out to the recommender system community. That is an ACM RegSys community. And we proved, they actually put RegDB as one of the top recommendation software that's out there. Before then, no recommendation software package used a database. All of them are kind of in-memory kind of techniques. So now, they actually, one of the techniques you can use, one of the software packages, that is actually, they benchmarked themselves, and they said it's good enough. It's RegDB, it's one of the, on the list here, on the RegSys wiki. And again, the code is on GitHub. We implemented this with Postgres, just a prototype with Postgres, and you can download it and play with it. A lot of people also are using it, like even in a production level, like startups are using it to do recommendation for their customers. Heterogeneity, other work. I'm just gonna go quickly here. What we did is like, how can you put a social network graph on a map? So, and query the data. Okay. So that fascinates. I'm copying this from Mark Zuckerberg, whatever you call it, cover photo, right? This one, and it fascinates me. I mean, because how can you query this graph with spatial data on the map? So this is also another project. We're not going to talk about the details. We have a short paper accepted at ICD that just scratches the surface of our technique here. Is again, we extend graph databases to support spatial data as well, like spatial attributes. And this touches, if you're working in database systems, on the work of hybrid relational graph database systems. So I'm not going to talk about details. I had some details, but I'm going to skip because no time. Okay. Are these the only challenges? Also, no. There is actually one major challenge that we always overlook. Like we go past it and then we ignore it. It's privacy. And this is actually the major challenge for anyone working. And whenever I talk to anyone, like in government or in the city, officials or anything, they care about that much. So just a quick, I'll be ending after that. So a quick example of this, again, the New York City taxi data. So if you run a query like this on the New York City taxi data, it will return this record. Here's what happened. Not so far from here, a grad student in Northwestern University actually did find timestamp photos of celebrities, okay, in New York City. Okay? And here we have a timestamp. And he could be able to run link attack on the data. And guess what? It's actually GeoDa and Leslie Mann. Like the grad student, figured that this is their picture. And the problem with that is that actually you can know the tip amount that they tipped the driver. And they're not very good tippers. And this is really bad, right? So yeah. Oh, it depends on how you define a good tipper again. I don't know, just like, yeah. So this is a huge like kind of challenge. One ways in our database community, one ways to do that is to use like anonymization techniques. There are some efforts in the database community, I would think like in mid 2000s, to do anonymization. So anonymization means that you make it, you reduce the details of the data, especially for high cardinality columns and longitude and latitude are high cardinality. So, but there are so many other techniques like differential privacy as well. I'm just stating this challenge out there because I think it's really important. It's really important in practice. So one last thing is the opportunities. A lot of the work that we do is related to open data initiatives. Existing governments and cities, when I talk to the city of Tempe, I talk to the city of Chamlix, like several cities, and they say one of the major problems is privacy, and another problem is they don't have kind of a tailored data infrastructure software for smart cities. And smart cities, geospatial data is really big, right? It is actually the main attribute they work on. Another thing is earth science. We have hundreds of terabytes from NASA. So how can you analyze all of this? There's a lot of challenges here and a lot of opportunities, okay? And NASA has like actually big interest in big data these days, okay? Take home, this is, today we talked about first how to do scalable or lightweight scalable spatial indexing. And then we talked about Geospark a little bit, how to do spatial data processing at scale. Scratch the surface on how to do interactive geospatial visualization. How to do recommendation. We talked about system RecDB. Also, we didn't talk much about geosocial graphs, like again the social network on a map. We talked about privacy and how important it is. And there are so many other challenges actually. So to scale the geospatial maps to the zettabyte kind of scale. I would like to actually thank all my collaborators, and this is just it's not all of them here. There are way more people that should be on the list, but I'd like to thank them all, and also especially my students that have been working really hard on implementing all these prototypes and working with me on that. So like that, I conclude my talk, and if you guys have any questions, and please don't hesitate to ask me a question.
Should we move the questions to happy hour? Yeah,
if I bored you enough with the details in this, there's an interesting part of my life. So I run, and I run the Rock and Roll Marathon last year. So this is an interesting topic also to talk about, right? Yeah. And I have all of this recorded actually on my smartwatch and everything. So there's a lot of location information in that as well. Yeah. So that's one thing. Yeah.
Great. Let's move the questions to happy hour since it's already 4 o'clock.
No problem. Thank you so much.
Thanks.